Here I have a steel wire. It is just a piece of metal, and if I connect it to a battery, I'll just draw the battery like that. I will obviously have some current flowing through this conductor. Now we've learned in the previous modules that if we have a current carrying conductor, such a conductor produces a magnetic field around it. And how does that magnetic field look like? Well, if I just raise this section of the wire here and show you, we've seen that the magnetic field of such a the magnetic field lines of such a current carrying conductor are actually concentric circles around this conductor. So if I just place the conductor somewhat like this on the ground, it's not a very straight one, so and draw the magnetic field around it, I would actually get circles like this, concentric circles around this. Let me just remove the battery here to make some space. I'll get concentric circles around the wire, something like that, and these concentric circles would represent the magnetic field lines around this conductor. Now the question here is that, so instead of just drawing them on the on a flat surface, let me just take a physical representation of the field lines. So I'll take something circular. I can take bangles, but I don't have bangles because I don't wear bangles. I can take this tape here to represent one of the magnetic field lines, which is just a circle around the current carrying conductor. And now the question is, what is the magnetic field? So if I add the magnetic field at all the points along this circular loop, what is the net or the total magnetic field along this loop? So that is the question. Well, in the last module we've seen that using the Biot-Savart law, I can find the I can take a small section of this current carrying wire, let's say this small section, and I can find the contribution that it has towards the magnetic field at any one point, let's say this point. So using that Biot-Savart law, I can actually integrate and find the total contribution of all the small sections of the conducting wire and find the net magnetic field at any one point due to the whole wire. Now in this case, I'll just assume that the wire is infinitely long to remove any complications and make the whole case more symmetric. So I'll just assume that this wire is infinitely long for now, just to make it simple. And so yeah, I can integrate all the effects of all these small sections of wire at any given point to find the net magnetic field at a given point. Now if I add the magnetic field at all the points around this circular loop, I will get the total magnetic field around the whole loop. Now without getting into the calculations using that involve a lot of integration and all that, I'll quickly skip all that and come to the directly the result, which tells me that the result, I'll just write it in the form of an integral. So if I integrate the magnetic field, which is represented by B, along this whole, I'll keep the conductor here, along this whole loop here, so let's say I'm integrating it along small sections of the loop, so I'll call those small sections dl. Remember, this is not the dl, this dl does not represent a small section of the wire, it represents a small section of this loop around the conductor. I hope you can understand that. So keep that in mind, it is not the small section of this current carrying conductor here, it is a small section of the loop that we're assuming. So this is just an imaginary loop around the current carrying conductor, and we have imagined this around this just to better visualize what's going on, right? And it'll all make sense in a moment. So if I integrate the magnetic field around this whole loop, and by taking small sections of the loop which are dl, this will be equal to, so what do you think the magnetic field along this whole loop, what will that magnetic field be proportional to? Well, obviously if I increase the current through this conductor, I should get more magnetic field, right? Stronger current means a stronger magnetic field around the loop, around the wire. So obviously it should be proportional to the current, and it so turns out that it is only proportional to the current, and we just have another constant here. Now that constant is obviously the very famous mu naught, or the permeability of free space. So this here is the permeability. You've seen that in the previous modules. This constant, which has a value of 4 pi times 10 raised to negative 7 newtons per ampere square. Yeah, so that is just a constant. Now what is permeability doing here? Well, if we think about permeability and permittivity are two constants that we'll be dealing in electric field and magnetic field while studying them. So permeability here is used in cases of a magnetic field, and it simply tells, it is a property of space. So the property of space or any other material. So permeability of free space simply tells us how much free space opposes the creation of magnetic field lines. And if I am taking the permeability of any other material, then that value tells us how much that particular material opposes the creation of magnetic field lines in that particular material. So I hope that makes sense. And similarly, if I am taking permittivity or epsilon naught, that is in the case of electric field, and that simply tells us how much that particular material, could be free space or any other material, how much does that medium or material oppose the generation of electric field lines in that particular medium or material. So I hope that is making sense. So I hope this makes sense. The magnetic field around this loop, if I integrate that by taking small sections dl along this loop, what I get is a product of current. So this magnetic field depends on the current through the conductor, larger current, larger magnetic field, and mu naught. So mu naught is a value that tells us how easy is it to create a magnetic field in that particular medium. So I hope that also makes sense to you. If it is easier to generate magnetic field lines in that particular medium, you will have more magnetic field, and if it is less easy or it's not so easy, then you'll have a weaker magnetic field. So even that makes sense. So this is the expression that we have, and one thing you need to note here is that, not so important at this level, but I'll just tell you, this is a closed integral. Now what does a closed loop integral mean? It simply means that the loop here along which we are integrating is a closed loop, which means it starts at this point. Let's say it starts at this point, it goes around and ends at this point. So the starting and ending point are essentially the same, which doesn't happen in other cases where if we integrate, let's say from one point to another point, the 2 points are different. But in this case, the starting and the ending points are the same. So we call it a closed loop integral of the magnetic field along small lengths along the loop called dl. Is that thing, if we calculate that should be equal to the permeability of free space or the medium we're in times the current through the current carrying conductor, right? So that is the basic that is how we understand this expression. Now in the next video I'll quickly simplify this whole expression. I don't want to make this video very long. I'll simplify this expression and tell you one more interesting thing about this law. And just to end it all, I'll just give you the name of this law. This is called Ampere's law, or Ampere's circuital law. And let me write the name, Ampere's circuital, because it deals with circuits. Circuital law, and it tells us the magnetic field generated by a current carrying conductor, and because that conductor is a part of a circuit, that's why it's a circuital law. And that's Ampere's circuital law in its mathematical form. But in the next video we will learn a few more interesting things about this law and one simple application of it. That's it for this video.